In this short video, I'll talk about the effect of medium coupling on CMUT bandwidth in a 1D array. So the idea is to look the CMUT cells as configured as 1D array, and there could be a multitude of such cells in a 1D configuration, and they can be receivers or transmitter, but an important effect that occurs when you are considering an array of such cells, which is, let's say, biased, or if you, let's say, are going to drive them by a certain electrical signal, let's say all of the cells are connected electrically in parallel and driven in phase, then the sort of current that the load derives, and if you compare this with the input voltage, then the Z input, which is equal to V input by I input, is very different from what you have for a single cell. Okay, so for, let's say, a single cell as a input impedance of Z1, for the same cell, which is let's say is at a certain distance D from the first cell, has an input impedance of Z2, then although the cells have the same geometry and have the same material, well, Z1 is nothing equal to Z2. It's different from Z1 and Z2 considering the effect of other cells in the same 1D array. Why this happens is that the cells, they tend to push each other. Okay, they're not only coupled in immersion, but when they are driven, when the membrane starts vibrating owing to the application of a harmonic signal, one cell pushes another cell, and this effect is the effect is called the coupling. It's called the mutual coupling, and it's not one cell that affects the other cell, but all of the cells are involved, and it affects the performance as well as the impedance of one cell that is being affected by the others. Okay, so let's have a look how it may affect the performance of a CMUT receiver configured as a 1D array. Now, for a single cell, this is typical small signal model in which the force is linear. So you can see this part of the model. There are two lumped components. One is the transformer that is being represented by electromechanical turns ratios NR, and then you have spring softening capacitance. So the force has been linearized. The model does not include the force that is proportional to the volt square of the applied signal. It's a small signal model, so the model assumes small signal conditions. Small signal conditions are that the applied AC signal is much less than the bias, okay, or the, let's say, where the electrodes of the CMUTs are biased. So you can see one of the small signal conditions over here. These are the geometrical parameters of a single cell, and you can see the harmonic signal VAC that you are applying over here is much smaller than V bias. Then, as a result of that, well, that is once you drive the cells, but as a small signal model, the idea is to usually obtain performance parameters like open circuit receive voltage or short circuit receive current, um, and that's very small. It's a very small signal, maybe microvolts, millivolts, in response to the incoming force at the caustic port of the model. Okay, so that's the caustic port. You have the radiation resistance, and then you have the incoming ultrasound signal. Okay, so if considering the rigid baffle considerations, if A is the radius, then that's it. That is twice pi a square into the incoming pressure. Okay, so due to this force the cell has on its membrane, you have a small signal voltage on its electrical terminals output, right? So this expected voltage is small compared to the bias. These are the small signal conditions, and this also further implies that the membrane displacement is going to be much smaller than the DC displacement. Okay, so if I may represent the expressions by capital subscripts, then these capital subscripts are DC subscripts, or these are DC quantities. And the small subscript in small letters are AC quantities. So the AC plate displacement is small compared to the DC plate displacement. Another way of looking at it is because the bias voltage is much larger than what you can get at the output. Okay, yeah. So I've taken a typical geometry where the radius is about 25 microns. Membrane thickness is 2 microns. Gap height is 0.25 microns, and TI is 0.35 microns. And if you can recall from my previous videos, the lump components of like COD is the electrical capacitance of the cell, okay, which is represented as C naught, and then a transcendental function in the in terms of normalized parameters. So that is xp by TGE normalized with respect to the effective gap height. Okay. If you want to learn more about the, because all of these lumped components are in terms of the geometrical parameters of CMUT, for example, LRM is the mass of the membrane. Okay, so you can watch the previous videos to learn about how they are derived and how they can be expressed in terms of these geometrical parameters. CRM is you can think of it as a compliance capacitance. It is modeling the what you may call it is the inverse of the Hooke's constant. Okay, it can be represented in terms of the Young modulus of elasticity of the material, which in this case is silicon nitride. So if I may write this as, if I remember this correctly, this is 9 1 minus sigma square a square divided by 80 pi y naught, where y naught is the Young modulus, and then Tm cube. Okay, so this Tm is the membrane thickness, and you can see if the membrane thickness is, you have a thicker membrane, then you have a smaller capacitance. It's less compliant. Okay, the compliance capacitance decreases. That means it's less compliant as a spring. The thicker membrane is difficult to move as compared to the thin membrane. Okay, thin membrane is more compliant, and it's also being represented in terms of modulus of elasticity. Why not? It also depends on the area, of course. So these are the lump components which are directly can be expressed in terms of the geometrical parameters. Okay, but then CRS is the spring softening capacitance, which happens to be the function of. So CRS is inversely proportional to, I would say, VDC square. Okay, it affects the series resonance of the circuit such that if you increase the bias, okay, then there is a series combination of CRS and CRM, and it's going to move the resonance. It's going to shift the resonance towards left. So that's the effect of CRS. CRS is going to shift down the resonance, okay, because CRM is not going to be affected by the bias, but CRS gets affected by the bias. Similarly, electromechanical turns ratios, they are proportional to VDC, and as you increase the bias, the turns ratio they tend to increase. One of the advantages of increasing turns ratio is that you might get larger short circuit received current if you are let's say employing the transimpedance amplifier on the electrical side. So the turns ratios increase and there's more current. Yeah, so if you are interested to look into the detail of this model, there are references on which this model has actually been derived. Now I'm just going to put them down in the description of the video. You can go ahead and have a look at these references. But the the point that I want to emphasize in this video is that the mechanical quality factor of a CMUT membrane, and in this particular example, I am simulating a silicon nitride membrane. Okay, so we have a silicon nitride membrane which is loaded with water. So the membrane is in immersion, is in water. Okay, and the material is silicon nitride, which has a density of about 3,000 kilogram per meter cube, and for water it's about 1,000. So why I'm saying these quantities is because you have this ratio over here. So what you do is, if you are interested in the mechanical quality factor of the CMUT, which is immersed in water, well then, if you believe that this circuit emulates the behavior of the single cell, then you can see it's a single section RLC. It's an RLC circuit. Therefore, the quality factor is omega L over R, and in presence of radiation reactance, which is the measuring part of ZRR, you have to include the complete reactance. So it's reactance plus inductive reactance and divided by the loss. The only loss over here is the radiation resistance. This can be, if you expand these terms, this can be expressed as such, and rho m over rho naught is the constant in times. If it is a silicon nitride membrane, then rho m over rho naught is 3. Okay, rho m is 3000, rho naught is 1000 for water. And then Tm over A, you can see it from yourself over here. This is your, so A by Tm is about 12.5, so it's 1 over 12.5. And the KRA is the resonance K, it's the frequency. R1 is the normalized radiation resistance. So you work this out, you have a constant from these terms for this particular geometry, and then you have a frequency term normalized with radiation resistance, and then you have x1 by r1, which is the ratio of the imaginary part of ZRR to the real part, okay, and that's what goes over here. So if you plot them with respect to Ka, you look at the quality factor, what you see is that first off, if you do the linear AC analysis for the circuit, you find out that the resonance occurs at about 7 megahertz. It goes at 7 megahertz. So we have to record the resonance at 7 megahertz. This is the input impedance of the cell. The red part is the reactance of the cell, which consists of all the capacitance is coming on the electrical side. So we are looking from here. So this is my zine. So yeah, this is my zine, and this zine has two parts. This is the imaginary part, and then you have the real part, right? So, but the resonance is at 7 megahertz, which means this corresponds to KRA. If you work this out for the radius of 25 microns, so K is the wave number, 2 pi by lambda. In water, this KRA works out to be equal to 0.73. Okay, about this much. And if you look at over here against KR, then the quality factor, if you do this analytically, and that's about 4.5. About 4.5. That's what is expected of this model. The quality factor, 3 dB bandwidth. Okay, whatever is the 70% level of the maximum. I'm just drawing this, as a stipulation that speculation that that this is the 70% of the maximum level, and the 3 dB bandwidth over here corresponds to the quality factor of 4.5. Okay, this is about 4.5. Yeah, so this is the story of a single cell, which is being represented by the linear circuit model. And for this linear circuit model, you can derive the mechanical quality factor in terms of its lumped components. That's again omega L over R, as you know from your basic circuit theory class. And that's how it works out. In you can plot this as a function of resonance K versus QM, and then you can also find the limits what you can have. For example, you can go below and you can find the maximum limit, but the point is over here, you can find the minimum quality factor that you can have, but in the new region of this curve. But the point is that we have a fixed geometry. That means we have a fixed A by Tm ratio over here, and then we have this the material properties are constant. Yeah, so we have a single point on this curve, which reflects the quality factor of 4.5. Okay, now just to show you that this curve or this model is valid, let's compare this with finite element model. Okay, this is a 2D axisymmetric. So I again have this circuit model, and apart from Zin, I have the sensitivity, that is the open circuit voltage with respect to pascals, the incoming pressure, PRI. Okay, so that's actually PRI. I've written pascals. Yeah, so the sensitivity is volts per pascals, and you can see it's about 1.2 into 10 to the power minus 4. Yeah, so it's like it's a millivolt per pascal sensitivity. It's 0.12 millivolts per pascal sensitivity that you get out of a single cell that is biased at 200 volts, and that's biased at 200 volts. It's not being driven by a harmonic signal. The harmonic signal driven was when you calculate Zin, And this is just for the incoming pressure in the medium, that you have this kind of open circuit receive voltage response versus frequency. Okay, at the resonance you have the maximum open circuit receive voltage, sensitivity about 0.12 millivolts per pascals. Okay, uh, comparing this with the FEM data, we have a problem that the bandwidth is much larger, right? I mean, you can look at this curve. It's the bandwidth is, I think, it's about, as compared to 4.5, this is about 1.3. The Q is 1.3. So we have a problem here, and I figured out that if you consider a 2D axis symmetric model, which is symmetric over here, yeah, you define this is the part of the transducer. This is a solid part. So this is the CMUT, and then you have the water column over here, which is about 10 wavelengths long. Yeah, so this is the water column, and yeah, so this is the solid part. Then you have about 2 micrometer of LPCVD silicon nitride over here, and then you have aluminum electrodes over these aluminum electrodes, and this is the gap height. This is the gap height. So what has gone wrong is that in the acoustic physics, when you define the physics of yeah, you have multiphysics in this modeling and in FEMS in COMSOL. There are boundary conditions that need to be defined. So first off, you can figure this out, that this is a perfect matching layer. This is a PML. Okay, so that you have a plane wave radiation conditions, and there's no reflections over here. The problem is this also needs to be defined over here as well. I mean, this also needs to be a perfect matching layer, but it so have gone into the model that this was a sound hard boundary. If you have a sound hard boundary, well, you have a problem, and this is the problem. The quality factor doesn't match. So the radiation doesn't converge to plane waves very soon. Well, very far in far field, yes, but then you also have reflection from the side. So to solve this problem and to match the quality factor and show that the circuit model performs up until the up to the accuracy of FEMS, what you need to do is to define this in the axisymmetric model, the perfectly matching layer, or perfectly absorbing boundary conditions on the surface of your radiation medium, right? Yeah, so this needs to be defined, and then you have the about the same quality factor. Yeah. The difference that you see is, well, I think this quality factor is much lower, a little less than 4.5. The problem over here is that when you do this numerically, the acoustic port in the circuit, the termination is in its own radiation resistance, which are Bessel functions of the form, if you remember, 1 minus 2 jx over, yeah, that's just something like 2x, if I recall this correctly, where x is Ka, right? Something like that. Yeah, if I can figure, if I remember this correctly, that was the real part, right? And the imaginary part is the Stroop functions. So those are in terms of Stroop functions, hx over x, something like that. Yeah, you have to see. I don't remember them exactly, but these are Bessel and Stroop functions, and in the circuit, those are analytics. You can see the solid lines. But in COMSOL, this is your well. First off, this is the red and blue regions are the compression and rarefactions in the medium, and if you consider you calculate the velocity on the interface of the transducer and your radiation medium, okay, from the solid mechanics part, then the pressure divided by the velocity is what you have in the broken lines from the FEMS. Okay, this one and this one. So these are the real and imaginary parts of that. So this is the radiation resistance that you get from FEM numerically, and there's a little difference. So let's say at 7 megahertz, we are looking at, yeah, 2 different values of radiation resistance, and therefore there is a little difference that you get in the quality factor over here. The quality factor is lower, which means the FEM has a higher radiation resistance. So yeah, that's what we are suffering here, I guess. Yeah. So this dotted line is FEMS. So the radiation resistance of FEMS is a little higher. I mean, for a piston radiator, which is being expressed as in a baffle plane, if you express that the caustic pore termination in terms of Bessel and Struve functions, if you calculate that numerically from FEMS, there's a small difference that shows up like this. But yeah, I mean, the circuit is still very close to the FEMS. Yeah, but for now, this is the case. Okay. All right. Now, this is the story of a single cell, and we have seen that for the given geometrical parameters and for the given biasing, we have the quality factor of about 4.5. Now, what happens when we have two clamp plates which are coupled in immersion, through immersion, I will say, and they are both receivers. They are sensing the waves, and it's not only that they, as a receiver or transmitter, they transmit or receive the acoustic pressures. They also tend to push one another, and that phenomena is the mutual impedance. That peculiar phenomena is modeled by the mutual acoustic impedance. It's important to uh, include the effect of the coupling because the cells in an array, they tend to push each other. They like to push each other. If the separation is larger, you don't have much of the coupling due to the cells. As you can see, if you have two clamped piston radiators separated by a pitch of, let's say, distance t, and both cells have the same geometry. Assume that the boundary condition is that you have a clamp plate on a bevel, and the plate is applied. It has been applied with a harmonic signal. Okay, so the plates are vibrating, and the distance d is not very large. Okay, they're close to each other. Then the radiation, mutual radiation resistance becomes a function of the distance as well as the geometry, which is the same. So the radius is the same, and then you have the same pitch. It also depends on the pitch. So it's an inseparable function of Ka, the frequency, as well as Kd. It depends both on the geometry as well as the distance. So Z12 is an inseparable function of K and Kd. However, its approximation, there's an approximation available in reference 2, you can see over here. And for let's say for low frequencies when K is less than 5.5, this function can be separated as such in terms of K and Kd. So you have two different functions where aka is a polynomial. So, okay, it's a polynomial in K where these coefficients are given in the following cited reference over here. Yeah, and I'll show you these coefficients, but this term that comes together with it shows that you have a sort of an oscillatory behavior. So if you plot this, G12 rho C normalized with the area, this is the area S, and then this is rho C, the characteristic impedance of the medium, then it's an oscillatory function which is decaying with increasing distance. But the important thing to note over here is that Z12 can go negative. You don't have a negative radiation resistance for a single cell, do you? No, you don't have. So if you look at for the blue curve and you compare this with the orange one, the dotted one, it doesn't go negative. It's an increasing function of frequency for low frequencies, and then it reaches a plateau region. But the mutual radiation impedance does goes negative, which means some of the cells are going to experience negative radiation resistance. What does it mean? It means that if you have three cells configured as a 1D array, which is separated by the same distance d, let's say, okay, so what happens is that one of the cells goes up, okay, the second cell goes down, the third cell, they have the membrane that is, so first and third cell are pushing the second cell to go 180 degree out of phase, and it goes down, so it experiences a negative radiation impedance, right? And that's vibrating out of phase with respect to the other two. So that's the idea of negative radiation resistance when you consider the coupling of cells in an immersion medium. So it's not only that they're experiencing the load from the immersion, but they're also pushing each other. And that's exactly what's going on in here at Z12. And Z12 happens to be an oscillatory function, which is in fact an inseparable function of both the geometry and the pitch. But yeah, for K, for low frequencies, K less than 5.5, as a reference is, you can separate these two functions. And AK is a polynomial. Here is the list of those polynomials, polynomial coefficients, pi, and this AK looks like this. So for low frequencies, the imaginary part is not important, but real part is still there. So this gets multiplied with the oscillatory function, which is over here. And that's how it looks like. Okay, so AK is sort of an amplitude of these oscillatory functions. Yeah, so the idea is, if you have the distance d, okay, of two cells, you can calculate Z12, right? You can calculate Z12. But what if you have a third? If I add the third element of the same pitch, then this distance is 2d, right? So all you have to do is just put this distance d as 2d, or if you have a fourth cell, then this distance is 3d, right, from the first cell. So then you have Z13, then you have Z14, okay, Z14, and according to the acoustic reciprocity, this is the same as Z41, right? So it becomes a matrix. So if you have, let's start with two cells. Then you have for both cells Z11, Z12, sorry, Z22. And if the cells are the same, the geometry is the same, then this is equal, right? But you have Z12. That is the effect of one cell on another. So the first cell, this is the first cell, and this is the second cell. So the acoustic port will be terminated as such that you'll have a matrix Z11, Z12, Z21, and Z22. And you can see the matrix is symmetric because Z11 is the same as Z22, it's the same cell, and Z12 is Z21. So the force that the cell number 1 experiences from cell number 2 is going to be the same as the force cell number 2 is going to experience from cell number 1. Yeah, so you can relate the acoustic force of the forces as such. Yeah, so this is a matrix, a symmetric matrix that relates to the velocities, because the true variable in the mechanical section is the velocity, right? I'm talking of this velocity current. Yeah, so this is the velocity current. And then this, you can have multiple cells. You can have V1, then you can have V2, then you can have a similar architecture of the circuit over here for cell 2. Yeah, so the transformer, and then you have spring softening capacitance. Yeah, this is V2. Then you have CRM, and you have LRM. Okay, although you have this, but I would like this to have terminated into a Z matrix. This is a Z matrix, and this Z matrix for two cells is Z11, Z12, Z21, and then Z22. You see the difference now is that the termination of the acoustic port is a multi-port. You need a multi-port termination so that the full matrix can be included. The effect of this matrix can be included as such. Now, these two piston radiators have different velocities, V1 and V2, and the force is related as such. This is the force. This is F1. This is going to be F2. Okay. And F1 is not only going to, I mean, if they're configured as transmitters and you apply a harmonic signal on the electrical side, then F0 is not only the amount of the force that the cell 1 is going to push or introduce into the medium is not only solely dependent on the radiation resistance or the self-radiation impedance of the cell, but it's also going to be affected by Z12 because the other cell is going to push the first cell, right? So what you're going to have is actually F1 is Z11 V1 plus Z12 V2, and that's how you include the effect of the second cell, right? And likewise, F2 will be Z22 Yeah, it will. If you look at this matrix, then Z21, V1 plus Z22, V2. Z22 is its own radiation resistance of the cell that the cell sees due to the loading of its membrane by the radiation medium over it, right? But you have to include the effect of the mutual crosstalk as well, and that gives some very strange or peculiar effects in arrays, which we are going to look briefly. And if we may start, let's start with the two cells. So these are two cells which are terminated into the in our 2 by 2 radiation impedance matrix, mutual impedance matrix for two cells coupled through the medium. The acoustic port in the circuit can also be simplified to a T impedance network. So yeah, I mean, these are the artifacts. So for two cells, you can do it like this because, yeah, if you look at F1, F1 can be, because if you're working on a circuit software like LT Spice or P Spice or whatever, you can, for two cells, it's simple. You can reduce such a T impedance network between the two port networks and terminate their acoustic ports as such. So F1, or if you look at this, is V1, what it becomes is V1, Z11 minus Z12 plus, yeah, then in this branch, currents from both of these branches are going to add up. So that is V1 plus V2 multiplied by Z12. Okay. So this term is going to cancel out with this one. And let's see what we get is V1, Z11. So the second term goes out, and what you're left with is V, V2, Z12. That's it. And if you consider over here, if you multiply this row with this column, you'll find out that F1 is Z11, V1 plus Z12, V2. So yeah, we have included the effect of the other cell. So the T impedance network can emulate the behavior of the mutual crosstalk of two cells, but this is only valid for two cells. For large number of arrays, this is not going to work. Okay, we have to consider a multi-port termination of acoustic port so that full impedance matrix can be included. So let's have a look how it looks like. Now these are two cells which are separated by a pitch of distance t, and I'll tell you this distance t is about 55 microns. Okay, whereas the cell radius is 25, or you can say the diameter is 50 microns. Yeah, so they're very close to each other. You can see the diameter of one cell is about 50 microns, 50 micrometer cell. And same goes for this cell as well. This is also 50 micron cells. So the only separation that is left is about 5 microns, right? 5 microns or less than that. Well, let's see. So you have two cells. And yeah, the distance is 55 microns. So that means half of this distance, that's going to be 25, 25, 50. Yeah, so you're left with 5 microns over here. So they're close to each other, pretty close. And you can see if you compare this with a single cell, what we have done earlier, single cell is like this, and you can see this occurs at about the level, the impedance level is about 4 into 10 to the power 5. It's about 400 kilo ohms. It's large impedance. And then yeah, it happens at 7 megahertz. So that's my reference. And I'm just going curious to see how the single cell compares with two cells which are coupled in a medium. And you can see if I consider this as a single element, okay, which has two cells, and I derive this with the harmonic signal, and then I have a current In, which I'm going to draw from the load, and this is Vin. So my Vin by Zin, Vin by In for two cells is going to look something like this. You see, it's a wider Q. The resonance Q increases, okay, as compared to the Q of the first cell, single cell, which is about 4.5. But if you wish to do this separately, so let's say you have different connection pads for each cell in your fabricated array, and if you want to consider the effect of different cells, then for each cell, then it's like this. And according to the acoustic reciprocity, it has to be the same. But the level is different. You see, the level is about 300,000 kilo ohms at the same frequency. Why? Because you're having it is wide bandwidth. It is wider in bandwidth. That means more better time resolution for medical imaging purposes as compared to the single cell, but as a transmitter, the power goes down. You see, the impedance level is not the same. It's different. It's low, right? It's low. Yeah, it's not the power output that I'm comparing. So yeah, I'm not showing the power. So maybe I should not be making the same statement, but you can see the bandwidth is increasing for sure. The bandwidth is increasing. So the impedance levels are different because there is a loading from the other cells. That's why we have to include Z12 or Z21. And according to acoustic reciprocity, Z12 is the same as Z21, which makes the matrix symmetric. So you don't have to calculate that again. And how you calculate Z12, I'll just say it again, that just include the distance over D over here for if the range is small, in the case less than 5.5. Well, you can have this approximation, just multiply AKA with Z12, and you have your Z12 matrix element, right, which is the same as Z21. If you have like 3 cells, 4 cells, just have this distance replaced by 2D, 3D, 4D, and construct your symmetric matrix, and then terminate your acoustic ports into the multiport network like this. And then you have you can see the effect of the bandwidth increasing with large number of cells. But that bandwidth is not going to increase forever. That's why I said it's strange or peculiar, because there's some optimization of the distance that you need to do if you want to go on increasing the bandwidth. And it's not only that the configuration is limited to 1D array. You can have the other configurations, like you can have a cell like this, and which can be surrounded by like a hexagonal, or let's say this is how many cells are there. 1, 2, 3, 4, 5, 6. Yeah, 6 cells surrounding a single cell. It's going to be different bandwidth. This, if you have for like let's say 7 cells, this is going to have a different queue. This configuration is going to have a different queue. So the effect of coupling is very much dependent on how the cells are placed, what are the distances, right? So that affects it. But since we are talking of 1D array, let's take another example. Now we have 3 cells, 1, 2, 3. And if you look at the real part, the first cell, what first cell is going to experience will be the same as what the third cell is going to experience, because first cell is going to have uh, the mutual crosstalk with the second cell, which is separated by distance d, and then it's going to be affected by the third cell, which is fixed at a distance 2d. And the same thing occurs for the third cell. So the third cell and the first cell are going to experience the very same, let's say, they will have the same forces at their acoustic ports, F1, F3, they're going to be the same. You can see from here, you can figure it out. But for the second cell, it's going to be different. It's a different story, because second cell is going to experience the mutual crosstalk from the same distance d for cell number 1 and cell number 3. But cell number 3 is going to experience force from d and 2d. Likewise, cell number 1 is going to experience force from d and 2d, so it has 2 distances. So you can see again Z12, and these are the same, this thing and this thing is the same. So it's just again a symmetric matrix, and for the same cells, for the same geometry and same material properties, the main diagonal elements are the same. But then it's a symmetric matrix. You don't need to include or calculate the mutual impedances for all the cells. You have to do for half of them. Okay. But yeah, you can see what's going on in here. So these levels are different. So cell number 2 is going to experience a difference. So F2 is different from F1 and F3, but F1 is equal to F3 because of the reciprocity. Let's see this in more detail, what happens in a 10 cell array. So we have this configured as 10 cells. So this is the same as distance D from cell 1 to cell 2. And this distance is 2D from cell 1 to cell 3, and this distance becomes about 9D from cell 1 to cell number 10. And if you can figure out what cell 1 is going to experience, it will be the same as what cell 10 is going to experience from all the other cells. Because cell 1 is going to experience the force from cell 2, which is at distance d, then 2d, then dot, 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 up until 9d. And likewise, cell number 10 is going to experience from d, 2d, 10d. So let's see if we have this. This is cell 1. This is number 1. And do we have, yeah, and this is cell 10. You can see the legend. So this is number 10 cell. They are the same, right? Same impedance levels. Likewise, let's consider cell 2. So where is cell 2? This is cell 2. This is number 2. This cell number 2 is going to experience what cell 9 is going to experience. And cell number 9 is over here. Okay. Likewise, number 8 is going to experience the same effect of crosstalk as cell number 3. This is cell number 3, and let's see whether the cell number 8 is. Yeah, this is cell number 8, and you can see the same bandwidth, the same impedance level, the same sort of, I would say, I don't know, spurious resonance. Yeah, a bifurcated sort of a resonance you can see over here. It's very similar because of reciprocity. So then again, if you go for cell number 4, this is cell number 4, and cell number 4 is going to be the same as cell number 7. So yeah, here's cell number 7. And then all you're left is cell number 5 and cell number 6. This is 5 and this is 6, and they are the same. You can see for yourself that these 10 cells are in linear 1D array. All cells are biased at the same voltage and are excited electrically in parallel in phase with 1 volt peak-to-peak time varying harmonic signal. So what happens is that because of reciprocity, the force ports, the acoustic port where the force is defined, is going to be the same for half of the cells, right? Because of the placements is as such. But you cannot have cell number 3 experiencing the same as cell number 1. Why? Because cell number 3 is going to see different distances as cell number 1 from each other. But cell number 3 and what cell number 8 are going to experience are the same. They have the same distances. Okay, so that's the reciprocity. So you can see the effect of, so I've simulated each cell separately, not as a single element. As a single element, it's a different story. I mean, if you consider this as a single 10 cell element, okay, 10 CMUT cells on a baffle plane, then it's going to be a different story. It's going to be a different bandwidth and impedance level. But single cell, let's say each cell has its own connection pad, then you have, because of crosstalks, because cells are close to each other, you will see different bandwidths and resonances like this. Okay, they can be bifurcated or trifurcated, more than that maybe. So that's the effect of mutual coupling in 1D array. So you don't have to terminate each cell in its own traditional distance, but you have to terminate in a complete Z matrix. Okay, yeah. So that's a comparison of the cells, multiple cells in a 1D array. So you have a single cell. You can, if you recall the level of the impedance level, that Q was about 4.5, and you can see the Q for 2 cell is lower. This is 2 cells, then 3 cell even lower. Okay, 50 cell is the smallest Q that you can get. So for circuit simulation, the acoustic port of CMUT cells, and you can see this. You can add as many number of cells you want, but your matrix is also growing. I mean, it's going to be n cross n matrix depending on number of cells you are going to have in a linear array. So n is the number of cells in an array. Okay, so let's say this is my nth cell and this is my first cell. So it's going to be, this is my 1D array. Okay, this is my 1D array, which is I'm going to derive by an AC source. That's it. So they're connected independently to a multi-port network where Zij and Zji are calculated for each distance according to the approximation given earlier. That's the porter's approximation. The connection of individual CMUT acoustic ports are made according to the above matrix. This is the matrix to include the coupling effect of all the cells, and you can see the effect of the bandwidth. Here it is tabulated. So for the single cell, well, I think this is 4.5 as we have seen earlier. Yeah, and the frequency is does not shift much. Like I think I should have put a line over here, but anyways, let's compare. Yeah, there is some shift over here. The shift of frequency um, is again I can put this blame on the acute effect of the mutual acoustic crosstalk, but it also depends on the size of the aperture size of the CMUT. How does it compares with the wavelength, right? How much the aperture size compares with the wavelength. If the aperture size is, let's say, lambda by 16, then this frequency is going to shift more. But let's say if this is like lambda by 2 or lambda, then it's not going to shift much, I guess, because the smaller aperture size CMUTs are going to, the effect of mutual crosstalk is going to be more prominent. There will be more spurious resonances that you're going to see. Okay, so yeah, okay. So what you see is regarding this figure, if you consider two cells, then the bandwidth increases from 1.23 to 1.81 megahertz. If you consider three cells, the bandwidth increases to about 2 megahertz. For 10 cells, in an array, that's about twice of 1.23. So you can see if you have one cell, you include 10 cells together in an array, and then you derive the impedance. Well, the bandwidth is doubled, okay? But this does not double if you multiply the number of cells 5 times in an array. So for example, for 50, it increases slightly to 2.51. So this effect of mutual crosstalk is not, do not think of that as that you're linearly going to increase the bandwidth. Well, it has its own effects, and it depends on the size of the cell, how much it is being affected. The quality factor you can see is dropping, but then this drop is not so steep if you go from 10 to 50, right? So you can see for 50, the bandwidth is large, but it's not much larger. So there is not much of a saving over here as you can do it for 10 cells, right? So that's the effect of the crosstalk that you have to consider. So if you have CMUTs as a linear 1D array for let's say a CMUT probe, then these cells are going to push each other, or they are going to affect one another, and you can drive them as receivers, or you can have biasings, or you can drive them as transmitters by applying a harmonic signal. Okay, but there's going to be effect of mutual crosstalk always, as long as they are very close to each other. But if you tend to increase the pitch, the distance between the neighboring cells, then this effect is it tends to vanish. Okay, because this is an oscillatory function, if you recall, right? But if the distance is increasing, KD increases, then this is not much. It's not going to affect much. Also, it also depends on the size of the cells. If the cells are small, then it's going to be affected more. The other thing that the bandwidth can for 1D array of CMUT cells of a CMUT array can be affected by is the backing. Okay, so you can have, for example, if you have a hybrid architecture, so that well, there could be PZT at its backing, let's say another transducer, or let's say there is a some acoustic backing port that you want to include, then you have to do this. The backing port is over here. This is acoustic backing, and you have to include the loss due to the backing, and that comes across the transduction force, which is over here. Not the transduction force, not the acoustic force. The acoustic force is over here. These are the acoustic ports. So you have to include this with the transduction force. So transduction force FR is over here. That's the force port. And you have to include across this port the effect of the backing impedance. This might further increase the bandwidth. You might have more time resolution, for better time resolution for the for CMUTs as sensors, medical sensors, or or suited for any other application. So theoretically, you can increase the bandwidth if you have the backing loss. This is a loss, okay. The only loss that we have considered so far is the because of mutual crosstalk and because by the bandwidth increasing and the self-radiation impedance of the cells. Okay, but if you consider the backings as well, then you can have let's say you have a hybrid architecture, you have a PZT as its backing. Okay, I mean, in applications when in a probe, for example, PZT could be a transmitter and CMUT can be a receiver. In that case, you might look at a wider bandwidth of CMUT, because CMUT is going to look down at the other transducer architecture and is going to consider its effect as a packing loss, and then you might have more bandwidth. Okay, so you have to, for example, a low frequency, or let's say if the high frequency is CMUT, because in in medical applications you have harmonic imaging, because a transmitter can be transmitting at a low frequency, and at high frequency you're going to receive it. So the low frequency is the transmitter part, high frequency is the receiver part. So in such an architecture, hybrid architecture, you can have a wideband response, much wider than this. Okay, you can have much wider than this. So that's just the story. But the important part of this video was to share with you the comparison of the bandwidth of multiple cells in a 1D array, and how they are affected by the mutual crosstalk phenomena. Okay, so that's all, and thank you for watching, and have a